So, hi Samantha. Hope you're enjoying your college visits. Hope it's nice and informative for you. We're going to be talking today about Taylor and Maclaurin's series, which is essentially extending our polynomials out to infinity in terms of numbers of terms. Before we do that, Charlie had a question.
Number 13.
13.
It was a geometric series one.
Uh-huh.
And so it was 1 over 1 minus 2x. And it was find R6 of x.
Okay.
Write a formula for that.
Mm-hmm.
And so I used 1 over 1 minus x and then plug in 2x. So then I got 1 plus 2x plus 2x squared plus 2x cubed plus 2x again.
Mm-hmm. So that's our T6. And that's going to be 1 to the 6. Are we looking for R6 or R5? I can't remember.
You said find the truncation one
For B6. Okay. So a 6-degree polynomial. Yep. And the phrase truncation error is just a synonym for the remainder. And the reason they use that phrase is that the idea is that the entire geometric series is the sum all the way out to infinity of the powers of 2x, right? And so we're now going to take that and we're going to truncate the geometric series at the 6th term, and the remainder is going to be everything else. So our remainder is literally the rest of the series, what we call the tail of the series. And the tail of that series, we observe, is a geometric series itself, which has a first term of 2x to the 7th, and it has a ratio of 2x, and therefore it sums up to a over 1 minus r. And that's it.
Because the back of the book just said the answer was 2 absolute value of x raised to the 7.
Huh. That's weird. Was it? Nope. Yeah, now this is the actual remainder right here. Not really sure what's up with that. Notice that it is entirely possible. This is the exact remainder, and it has to be. You see, it has to be that. So I think they're just wrong. Good. Any other questions? Okay. Well, let's get to it. Our story so far has been that we can estimate a function, f of x, with a k-degree Taylor polynomial. And the important features are, first of all, that you should be able to write the k-degree Taylor polynomial in rolled up or unrolled form. So in rolled up form, we're going to sum starting at 0 and going out to k, right? So it's a k-degree polynomial, and my coefficients are going to have a special form, and what is that special Taylor form? Fk? Maybe we should write it in unrolled form first. So if I write it in unrolled form, my first term would be none of the above. F of c, exactly. The f of c here is my starting point, just like it is for the tangent line, right? And then what's my next term?
And prime.
Times times x minus c. And there's my tangent line, my first degree term. And now what's my second degree term? Double prime of c times x minus c squared over 2 factorial, which reminds us there's an invisible over what here? Over 1 factorial and over 0 factorial. Okay? And then plus that. And what is my last term going to be? I'm barely hearing you.
Times x minus c
Okay, good. Students often find that they can write it out in unrolled form easier than they can write the rolled up form. Let's now take this unrolled form and work it backwards to here. Remember that n is our index, k is the last value, so it would be sort of surprising if k showed up here. So, as I go through, which of these quantities get indexed? Let's build this up. The prime number, that's right. So that means we're going to use the nth derivative. And we're going to evaluate that nth derivative where? At C, at the center. And that's our term there. Alright? What else?
Over and right.
Is it n minus 1?
No, and
It is in factorial. That's exactly right. And then?
minus
Uh-huh.
n minus 1.
Is it n minus 1?
No, still no, n.
It's still n, that's right. Everything is to the n power and we start at 0. Yep. Everything is in terms of n and we start at 0. You want to practice writing out the rolled up form and thinking through that language just a couple of times so that you can see what the language means. It's not hard, it's just that if you don't think through what the language says and what it means, then you're going to get confused. You're going to put k's in there, and n minus 1s, and you're going to evaluate at x instead of c, and okay? Alright, so that is our Taylor polynomial. Then we discovered yesterday that we can actually say something about the remainder when I evaluate the Taylor polynomial at x. So the idea here is that I have a center C, and I'm going to evaluate at some x, which may be on either side of C. And when I do, what I find is that there is some t somewhere between C and x, so that the remainder is exactly equal to the k plus 1th derivative at t times the quantity x minus c, the k plus 1 k plus 1 factorial. We don't know where t is. And so because we don't know where t is, then what we're going to have to do is to use a worst case assumption. And that worst case assumption is that the remainder can be no worse than the maximum possible value for t's between c and x of the k plus 1 derivative at t times x minus c to the k plus 1 over k plus 1 factorial. And this was the Lagrange form of the remainder, or the Lagrange mean. And that was our story from yesterday, complete with 20-minute proof. Easily the hardest proof all year. Okay, now, here's an interesting thought. What if I take my Taylor polynomial and I let k go to infinity? What happens then? I don't know. Some different things might possibly happen. One thing might, certainly I'm going to get an infinite number of terms, blah, 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 right? It might be the case that when I go out to infinity, that those terms added together might give me an exact representation of a function. Can you see that? That it's at least possible? Because as I add on terms, my estimate gets better and better and better. He was here and now he's gone. He's probably in the media center. In theory, my estimate should get better and better and better as I add on more terms, right? So, in theory, maybe as I go out to infinity, my series becomes perfect. That would be delightful. Another thing might happen, though. It might be the case that as I go out to infinity, something weird happens to my series and it blows up. How could I tell? Well, I think a great way to tell will be to take a look at the remainder. If the remainder goes to 0, then my series becomes perfect. And if the remainder does not go to 0 in some way or another, then it's really hard to tell what's going on. What's that? If the remainder goes to 0?
I don't see how that happens.
Good. Well, let me actually do that then. Keep in mind that our basic premise is that the function is equal to the Taylor polynomial plus the remainder. So if the yeah, that's right. So if the limit as the remainder of the remainder is 0, then this would imply that the limit as k goes to infinity of tk must be equal to f of x, and therefore my tk would be an exact representation of the function. That's pretty cool. I like short proofs like this.
Yeah, it feels like all you had to do was write it on the top.
Yep, that's exactly right. Okay, so let's take a look at a couple of functions and see how that works out. There are 3 functions in particular that we want to know these series for. I'm going to call them Taylor or Maclaurin series. Maclaurin series would be ones with a center at 0. And the first one is the Taylor or Maclaurin series for e to the x centered at x equals 0. And what's delightful about this series, of course, is the property that e to the x has, which is that all of its derivatives are equal to e to the x. And therefore, all of its derivatives at 0 are equal to 1. So we can immediately write that the series for e to the x, and I'm going to use a symbol here, corresponds to, this corresponds to means it might be equal to if the remainder goes to 0. Corresponds to sum from n equals 0 to infinity of flesh 1 over n factorial times x to the n. Notice here that I've used the Taylor form, and the nth derivative at 0 is 1, and of course x minus 0 to the n is just x to the n. If I unroll this, then I get 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x dot. And of course we'll put our nth term in. And there it goes. This is possibly the most famous series in all of mathematics. Now our question is whether or not this convergence is, this correspondence is really an equality. Does e to the x actually equal this number? Does it equal this number for all x's? Does it equal the z to the x equal to series, I should say, for all x's, for some x's. Let's take a look at the remainder. The remainder, rk of x. Wow, that was bad. Is going to be bounded by the max for t's in c to x of the k plus 1 derivative times x minus c to the k plus 1 all over k plus 1 factorial. And what we observed is that because e to the x is an increasing function, therefore that max is actually going to happen at e to the x. Okay. So now, having constructed this, we are interested in this question. What is the limit as k goes out to infinity of this remainder? Now, this looks like an awful expression, but it's actually not as bad as it looks. Keep in mind that x here is a fixed point of evaluation. So on my number line, I've got a center, and I'm going out to some x, and I'm going to evaluate the series at that x value, and when I do, I've got some number here. What I'm looking at is, as k goes out to infinity, as I continue to add on terms, I wonder what happens to this remainder right here. So anything just involving x, like e to the x, is a constant with respect to the limit. So what I'm really looking at is just this limit right here. Okay? Yeah, you're right. So now we wonder, what is this limit right here? I'm going to make an intuitive argument. I could argue it by induction, but I'm going to claim that this limit right here is actually equal to 0. Now, why is that? Let's compare x to the k plus 1 and k plus 1 factorial. X to the k plus 1 is going to be x times itself, k plus 1 times. Right? K plus 1 factorial is going to be 1 times 2 times 3 all the way out to k plus 1 times k plus 1. So both of them are products of k plus 1 factors. But x to the k plus 1 is going to be the product of k plus 1 identical factors. No matter how big x is, I'm going to be multiplying the same thing k plus 1 times. K plus 1 factorial is going to be the product of ever-increasing factors. So that k plus 1 factorial starts slowly, but eventually I'm going to be multiplying by numbers that are much larger than x as k goes out to infinity. And so because of this, x to the k grows much slower than k plus 1 factorial. And as a result, that means that as k goes out to infinity, this limit is 0 for every x value that I get. Now that's a plausibility argument. If you want me to do it formally, I can do it by induction. But I think you can see it. Does that make sense? Here? Well, it is. See, here's x2 and x1.
But I don't understand why it's just 1. Right? X raised.
Oh, no, I'm multiplying x times itself k plus 1 times. That's what the x1 means.
Oh, okay.
Yeah. What I'm doing is just rewriting x to the k plus 1 the long way, that like we did in Algebra 1, so that we can compare the factors here. So for example, if x is equal to, let's say, 5, then 5 to the 600, and that's a relatively small number, would be 5 times itself 600 times. Meanwhile, 600 factorial is going to be 1 times 2 times 3 times 4 times 5. Oh, look, my terms just caught up to 5. Times 6 times all the way up to 600. And clearly, the difference between those is going to be substantial. We're going to end up growing much faster. Okay. Now, what does it mean for us? Because the remainder goes to 0, this means that our Maclaurin series represents e to the x for every value of x. So what we have then is a nice result. We can say that this is e to the x. And in fact, in advanced textbooks, when you study functions, very often e to the x is actually defined as this thing. And then all the properties of e to the x are derived from that series. For example, I'll just give you one of them. Let's take a look at the derivative of e to the x by considering the derivative of the series. And let's go term at a time. The derivative of 1 is 0. The derivative of x is the derivative of x squared over 2 is x. The derivative of x cubed over 3 factorial is 3x squared over 3 factorial. You got it. The derivative of x to the n over n factorial is x to the n minus 1 over n minus 1 factorial, which is just another way of relabeling that series. And lo and behold, the derivative of e to the x is itself. That's pretty cool. Really profound, actually. Very, very impressive. Let's take a look at the series for cosine. F of x is equal to cosine x. And so now we're going to start computing some derivatives. These derivatives at first look like they're going to be a pain, but then something wonderful happens. And that is that we start getting repetitions. What's our period for our repetition? Yep, that's right. Every 4 derivatives, the cycle starts over. And furthermore, if I evaluate at the center x is equal to 0, then my even numbered derivatives are going to give me 1 or negative 1, and my odd numbered derivatives are going to give me 0. I want you to notice an important thing, and that is that cosine is even. And because cosine is even, its odd numbered derivatives are odd functions, and its even numbered derivatives are even functions. And every single odd function has the property that it has to go through the point 0, 0. It has to go through the origin, because f of 0 has to equal the opposite of f of negative 0, which means that f of 0 has to be 0. Therefore, that means that all of the odd coefficients for any even function will be 0, which means that an even function for any even function, all odd coefficients are necessarily 0, which means means that an even function will always only have a series that involves even powers of x. How cool is that? That's the cool stuff. Well, at this point, we can start generating our series. We're going to get cosine of x corresponds to 1 plus no x minus x squared over 2 factorial plus no x cubes plus x to the 4th over 4 factorial. And then our pattern will continue, minus x to the 6th over 6 factorial plus dot, dot, dot. Now, if we were to try to roll this up into a sum, then we're going to sum up from n equals 0 to infinity. And let's see here. If I number the terms according to the original, then I have a hard time fitting those zeros in, right? So what I'm going to do is I'm going to number the terms just according to how many terms I have here. So this is going to be term 0, 1, 2, 3. And if I do that, then the exponent is clearly twice that. So that I get x to the 2n here. And the factorial on the bottom is going to be 2n factorial as well. And now I can make the sign alternate with the famous -1 to the even power. So there comes my alternating sign. Does that make sense as a rolled up version of this guy right here? We're providing only even exponents and only even factorials, and we're doing the alternating sign. Let's check whether or not this correspondence is equality. So that Rk of x is bounded by n plus 1 derivative. K plus 1 derivative times x to the k plus 1 over k plus 1 factorial at some t. And that's going to be max over all t. I get a little sloppy with this. There it is. And so now I don't know what my k plus 1 derivative is going to be. It could be cosine, it could be sine, it could be negative cosine, it could be negative sine. However, I do know that it's bounded by 1. And so therefore this is definitely less than or equal to the value x to the k plus 1 over k plus 1 factorial. And so now, as k goes out to infinity, then we see a limit that we've seen before, which is the limit as k goes to infinity of x to the k plus 1 over k plus 1 factorial. And because k plus 1 factorial grows much faster than x to the k plus 1, therefore that limit goes to 0. And we conclude that for all x, cosine of x is exactly equal to our series here. And we can replace the corresponding sign with equality. Here. Yeah, so this term, this factor right here, the k plus 1 derivative of cosine, is going to be one of 4 functions. Sine, cosine, negative cosine, negative sine. It's going to alternate between this. However, in all cases, the largest possible value of that function can be no bigger than 1 because of the range of sine and cosine.
Okay, so then it's actually there. But
Bounded by 1, that's it. So actually, we're making progress in terms of getting pretty fast at evaluating these series. And that's an encouraging sign. Let's do one more, which is going to be sine of x. And it's going to come as no surprise that sine of x is also going to give us equality for all x's. In fact, why don't you guys go ahead and leave the charge there, generate your derivatives, and generate your series, and then we'll do the remainder together. Go. Okay, So, welcome back, and what we found is that the coefficients are all odd for the simple reason that because sine x is an odd function, that means that its odd derivatives, the first, the third, the fifth, are going to be even functions. And the even derivatives, the 0, the second, the fourth, the sixth, are all odd functions. And as we observed before, means that the coefficients of those even derivatives must be 0 because the function is 0 at the order. It is 0 at x equals 0. So what we discovered then was that sine x is equal to, hopefully you discovered, that f of x corresponds to, or sine x corresponds to, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus blah, blah, blah. Is that what you found?
What's the h and
Oh, the a sub 2n, so the even numbered Taylor coefficients.
oh,
Yeah. Were those the coefficients that you found? Excellent. Okay, now the question is, how do we write the general term? But you have to make them odd. How do we make them odd? 2n plus 1. Exactly right. So we're going to have x to the 2n plus 1. We're going to have 2n plus 1 factorial. Anything else? We make it alternate with negative 1 to the n. And we wonder, should this be negative 1 to the n plus 1? Let's just check. When n is 0, then we get a positive 1. So that's actually correct. Yeah. Yeah. And the way to figure that out is to just check the first term. And now we can actually write it up in rolled up form using our general term. And we can use legitimate equality because, oh wait, we haven't proved that yet, but we're about to. X minus 0, to the k plus 1. That's horrible. I'm in too much of a hurry. Slow down, people. Over k plus 1 factorial. And the same logic that we had for cosine works for sine. That the function, the k plus 1 derivative, has 4 choices. It could be cosine, it could be negative sine, it could be negative cosine, or it could be positive sine. But all of those are bounded by 1. So that I am safe in saying that this error bound is definitely less than or equal to x to the k plus 1 over k plus 1 factorial. So that the limit as k goes to infinity of r k of x is again equal to 0. And we conclude therefore that sine x has that value for all x.
what is the n equals to negative?
So when we put in n equals 3 in here, then that would correspond to our 0, 1, 2, 3 term, and that should give us x to the 2 times 3 plus 1 is x to the 7 over 7 factorial times negative 1 to the 3rd. So we predict that our next term after this should be minus x to the 7th over 7 factorial, and that fits the pattern nicely.
Oh,
So n equals 3 is not the exponent here.
yeah.
This is n equals 1. Yeah. Okay. Two things I want to do. One is to briefly show you what we've been doing, which is how to use these series to construct series for other functions. Oh, there's too much to do in 10 minutes. Let's see here. Very quickly. What is the derivative of sine x? Well, the derivative of sine x is going to be the derivative of its series, just like so. And so if I now go through and take derivatives, lo and behold, I get 1 minus 3x cubed over 3 factorial plus 5x to the 4th over 5 factorial. Yep, you got it. And that gives me x to the 2n plus 1 minus 1 times 2n plus 1 over 2n plus 1 factorial, which is exactly equal to the series for cosine x, which is very delightful. And you can bet dollars to donuts that the derivative for cosine will be exactly the opposite of the series, the derivative of the series for sine, which is really cool. Which leads to a question, why didn't we just define sine and cosine like this to begin with? Unfortunately, because we needed the derivatives of sine to generate these coefficients. However, I'm currently reading a geometry book that starts by defining sine and cosine in terms of their series. And then you like generate all the properties. Okay. It's a thing. So related series. Suppose I have a function such as f of x equals e to the negative x squared, and I wish to know the Taylor series for this. Well, I could, if I wanted to, try to take derivatives and start looking for a pattern. No. I want to leverage the series that I already have and write this as x times the series for e to the x evaluated at negative x squared. Oh, let's use names. And when I do, I get x times all this, which is another way of saying let's see here, negative 1 to the n power, just from simplifying this, times x to the 2n, all over n factorial. And then we're going to multiply the x through to get x minus x cubed plus x to the 5th over 2 factorial minus x to the 7th over 3 factorial. And the general term will be negative 1 to the n, x to the 2n plus 1 over n factorial. Just like that. Does that process make sense? It's just a grand exercise in substituting. Now, working backwards can be a little more challenging. I want to consider this value. I can imagine this being like a multiple choice question. Let me let you catch up. What is the value of 1 minus pi squared over 2 factorial plus pi to the 4th over 4 factorial minus pi to the 6th over 6 factorial plus negative 1 to the n pi added the 2 in over 2 in factorial 7. Our first thought when we look at this is, I have no idea. I can't add up powers of pi out to infinity and find their value. My second thought is, hey, maybe this is a series that I know and love. And so I start examining the coefficients, the terms carefully, and I start looking for a series that I know and love. And what I observe is alternating signs and only even powers of pi divided by that same power factorial. That strongly reminds me of the even function whose Maclaurin series is the series for cosine. So that this entire value is simply cosine pi, and all these numbers add up to -1. Boom. It's pattern matching. I see the pattern for cosine, and I conclude that this is cosine pi. And once you get good at it, you can do all sorts of stuff. 1 minus 1 plus 1 over 2 minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial, etc. I look at this and I think, I have all the powers of -1 represented divided by the coefficients factorial, the indices factorial. That reminds me of the series for e to the x. 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And it would be e to the x evaluated at -1. So that all of this adds up to 1 over e. And it's just a matter of recognizing patterns. But to do that, we actually have to know those patterns. And what are the 3 important patterns that we've seen so far? E to the x, sine x, and cosine x. So you have to become familiar with those to actually be able to use them. And the way to become familiar with them is to derive those patterns for yourself. And once you do that a couple of times, you'll be fine. There are 2 other patterns on the horizon that we kind of know about already. One pattern is the geometric series pattern. Notice the compare and contrast with the e to the x pattern. What's missing here other than my one term of x? What's missing in each of these terms that makes it not e to the x? The factorial's in the bottom, that's right. And that's going to influence the interval of convergence. And then its integral, when I integrate this, then I get x plus x squared over 2. Notice not factorial. And so this is a final pattern that we would want to be able to match. So we really have 5 different patterns that are familiar to us. And our goal is going to be to get really familiar. See you later.